Welcome back to Math 104. When you fill in the rest of the entries in this table to see the breakdown of our ideal data set of 100,000 drivers, these are the results. So where did this 1,190 come from? This is 7%, so 0.07, 7% of the 17,000 people who are in this age group, so 0.07 times 17,000 equals the 100,190 people who are both in the age group and had an accident. That means that the remaining 93% of 17,000 people equals 15,810 people. Those drivers are in the 40 to 49 age group and didn't have an accident. Similarly for the rest. The first 5 rows of this table are directly based on applying the given information, where the given information is what was in this table. Before we leave the table of given information completely, let's notice that the sum of the unconditional probabilities has to equal 100%. But the sum of these conditional probabilities has no meaning, because this 15% is 15% of something different than this 9% is 9% of. And this 7% is 7% of something different again. These percentages are not comparable to one another. They have no direct relationship with one another. Their sum is irrelevant. We can essentially forget about the form in which the information was originally given, and now work solely with this table with this ideal data set of 100,000 drivers. What percentage of the overall population had accidents last year? In other words, what is the probability that a randomly selected driver had an accident last year? This is an unconditional probability. It pertains to the entire population. One of the benefits of writing out the table is that we find out the total who had an accident just by summing this column. It equals 11,270 drivers. Thus the probability is 11,270 over 100,000 that a randomly selected driver had an accident. That equals 0.1127. Now some conditional probabilities. A driver calls up to report having been in an accident. What is the probability that the driver is 40 to 49 years of age? Let's stop and think, which conditional probability are we computing? It involves being in an accident. It involves being 40 to 49 years of age, but we have to be careful which way the conditioning goes. The known information about this driver is that of having been in an accident. Thus we are conditioning on having been in an accident. We are looking inside this column, which means that the denominator will equal 11,270. Ultimately, our question is, what is the probability that the driver is 40 to 49 years of age? There are 1,190 such drivers out of 11,270. That equals approximately 0.1056. 10.56% of those who had accidents were in this 40 to 49 age group. A driver calls up to report having been in an accident. What is the probability that the driver is at least 40 years of age? We are still computing a fraction out of 11,270. We are still zooming in on those who have been in an accident. That is the known information about the driver. Now, how many outcomes are in the event is at least 40 years of age and had an accident? That is the union of all the outcomes in these 3 events. Out of the 11,270 drivers who had an accident, the drivers who count towards the event that we're discussing numbered 1,190 plus 1,500 plus 3,510. That equals 6,200 divided by 11,270, which is approximately 0.5501. Knowing that someone has been in an accident, there is a better than 50% chance that the driver was at least 40. Now that we have thought a bit about conditional probability and independence, let's look at another way of testing 2 events for independence. We recall that if E and F are events, and the probability of F is greater than 0, then the probability of E given F makes sense. We recall also that if it turns out that the probability of E given F equals the probability of E, that is, the after-the-fact probability, after knowing that F has occurred, is the same as the before-the-fact probability, before we knew anything about F, then we say that E is independent of F, since knowing about the occurrence of F has no impact on how likely we think it is that E occurs. If E is independent of F, then this expression, which by definition is the probability of E given F, So probability of E intersect F divided by probability of F, that's just our definition of conditional probability. If E is really independent of F, then this thing really equals probability of E. We can manipulate this algebraically by multiplying both sides of the equation by P of F. But this causes P of F to cancel from numerator and denominator in this expression, and what we are left with is probability of E intersect F equals probability of E times probability of F if E and F are independent of one another. This formula is important. Not only is it a true statement about independent events, but it gives us a new way of testing whether events are independent. So here is a useful way to test whether E and F are independent, and that is to compute probability of E intersect F, also compute probability of E times probability of F, and see if these two quantities are really equal. If this quantity, probability of E intersect F, really does equal this product, P of E times P of F, then E and F are independent of one another, and otherwise they are not independent of one another. Here is an example. Previously we looked at the following data relating the events A randomly selected person has asthma, and M, the event that the person is a minor, in other words, under 18 years old. We computed that the probability of A given M, focusing on M, on these 251 people, and looking at what fraction of them had asthma, the probability of A given M equals 22 over 251, which equals 0.0876 approximately, while the probability of A equals 76 over 1,000, or 0.076. Now recall how we thought about this. Are A and M independent of one another? No, they are not independent of one another, since the probability of A given M, the after-the-fact probability, does not equal the probability of A itself, the before-the-fact probability. Therefore, the occurrence of M does influence how likely we think it is that someone has asthma. That was our first definition of independence that followed a certain logic and made sense. Our new way to test the independence of A and M is to compute probability of A intersect M, and compare that to probability of A times probability of M. Pause the video and do these computations and make the comparison. Are A and M independent? Probability of A intersect M equals 22 over 1,000. This is an unconditional probability. The 22 here is divided by the full 1,000. This is 0.022. On the other hand, probability of A times probability of M equals 76 over 1,000. We see that here, 76 out of 1,000 had asthma, times 251 over 1,000. This equals 0.019076. We see that the probability of A intersect M does not equal 0.019076. Therefore, the answer is no, they are not independent of one another. A is not independent of M is not independent of A. We can actually say a little bit more. Think what the probability of A intersect M means. It measures how frequently these events occur at the same time, how likely they are to occur together. This product tells us how often they should occur together if the events were really independent. If A and M were really independent, then when we computed the probability of this intersection, we would have gotten the same thing as P of A times P of M. Since A and M occur together more frequently than they should if they were really independent, we see not only that they aren't independent of one another, but also that the occurrence of one increases our assessment of the likelihood of the other, because they occur together more often than they would if they were independent. Please go on to the next video.